So before we get started on some mathematics, we ought to say that we're really grateful for Trinity College here in Cambridge, who have funded this event and others like it so that they're free to you as participants. And we're very grateful to them. It would really help us as presenters if you could please make sure that the way that your name is displaying is the way that you'd prefer. So if you'd like to change anything, do click on the three dots alongside the video window and rename yourself. It just helps if we'd like to refer to you in the chat. We will be using the chat throughout this afternoon to encourage you to share your ideas, participate in the mathematics as we work together. But if at any stage you have a much more general question, which doesn't necessarily relate to the maths we're working on, do post it there as well, because we'll do our best to answer. And those of us who aren't immediately presenting will be keeping an eye on the chat throughout the afternoon. We would like to just remind you that you've agreed to participate with our code of conduct this afternoon, so please be respectful for everybody, and then we'll all be able to enjoy the event. So the aim of this afternoon is to work on some mathematics together, to share with you the current problems in the latest secondary feature on NRICH. Now, as I mentioned, I'm the primary coordinator of NRICH. So at this point, I'm actually going to hand over to Charlie, the secondary coordinator, who is responsible for those tasks, and he's going to guide us through them. Thanks, Charlie.
Thanks, Liz. And what I'm going to do straight away is share my screen. So hopefully you'll be able to see that on your screen. Let me just check that. Okay, so I've got the NRICH homepage there, and I'm going to go straight. I could go to either secondary students or secondary teachers page to show you the current feature. I'm going to click on the secondary teachers lozenge, and here's the latest feature. So all the problems we're going to talk about today appear here in the secondary teachers feature, though later with Claire, we're also going to talk about the post-16 feature. So here we go. So Liz wanted to thank Trinity College. We also want to thank Heilbronn Mathematical Institute, who have been funding these resources that we've just produced. And they've got a sort of number theory kind of feel about them. So they're linked to the curriculum, but perhaps not quite what gets encountered by all students, or not for very long. So we think that mathematically interesting problems. And the first problem that we want to introduce you to talk about is dozens. And you'll see here that it says age 7 to 14. So both Liz and I think that they're suitable at the top end of Key Stage 2 and at Key Stage 3. So Liz and I have worked on this. Some of you may have used the problem dozens before. We've done some work on it, we've revamped it, it's got a new interactivity. So we're quite excited about the new possibilities that it offers. So that's the first problem that we're going to talk about. So let me click on this and show you what this looks like now.
Charlie, could I just interrupt very briefly? I noticed you're actually still logged in to NRICH as we have logins so we can edit the site. It might be worth logging out so it just is not quite so. Sorry.
That's fine. No, thanks for pointing that out. So I'm going to the latest feature and clicking on dozens again. Is that better?
Yeah, that's great.
Let me move this as well. Okay. So for those of you who've seen dozens before, to start with, we're going to start in exactly the same way as the original problem did. So Liz, you could be my guinea pig for this. I want you to produce a 3-digit number, which is a multiple of 2. You've got to use the digits 3 and 7, and then a third digit of your choice.
Okay, Charlie.
And the challenge is to produce the largest possible 3-digit.
Right. Okay. Ooh, I like the sound of this. Okay, so if I want a multiple of 2, I know multiples of 2 are even. So I know that the units digit or the ones digit of the number has got to be an even number, and I've only got odd digits here. So so straight away that tells me that I'm going to have to pick an even digit to accompany the 3 and the 7. And that even digit is going to have to go in the units column. And if I want to make it large as I can, that's presumably got to be an 8. And so if I'm left with 3 and 7, I could either have 378 or I could have 738. So I think I'm going to go for 738.
Okay, here we go. 738, and we can check. And that is indeed the largest multiple of 2.
Okay.
If you hadn't understood the instructions because I hadn't given them correctly, and you'd thought that you had to put these 2 digits in the order in which they appeared there, and you'd given me 378, then the feedback you would have been given is that you did have a multiple of 2, but that there is a larger one, and so there's an option of trying again. Okay, so this is very easy for you. So instead of setting up another one with multiples of 2, let's go straight to multiples of 3. So I've clicked on the 3 here. Again, you're given 2 digits. You've got to find a third digit. And again, you're trying to work out the largest multiple, a 3-digit number. And this time it's a multiple of 3. So just before you start, can you just remind us what the rules are for multiples of 3?
Okay, so I think if I want to know whether a 3-digit number is a multiple of 3, I'm going to sum the 3 digits. And if that is a multiple of 3, then I know my 3-digit number is a multiple of 3.
Right.
Okay. So I've got to choose another digit to put with the 3 and the 4. So 3 and 4 makes 7. So I guess the next available multiple of 3 after 7 would be 9, and that would mean that I would need 2, but I'm trying to get the largest one. So could we try that, Charlie? What would happen if I did put 342 or 432, because I know 432 is bigger.
Okay, so the digits there are up to 9, so that's going to be a multiple of 3.
Yeah. Okay.
You're told there's a larger one.
Okay, so so let me think. If I want to add up to 4 and 3 is 7, I said. So let me see. The most I can add is 9. 4 and 3 and 9 makes 16, I think. 4 and 3, yes. 7 and 9, 16. So the nearest multiple of 3 is going to be 15. So what about if I put an 8, Charlie?
Okay.
So an 8, so I think 843.
I think that's going to work. Yes.
Whew. Good.
Okay. So
those of you watching at home, I apologise for the painful thought processes that you were witnessing as this. I am clearly a good example of yeah. Well, I'm not afraid to talk about to articulate what I'm thinking, even if I'm worrying at the same time that it's not totally sound reasoning.
Okay, so I think this is the time now to ask everybody else to get involved. So I'm going to click on 6 next, and we're going to do multiples of 6. Mm-hmm. But before we do that, could everybody think about what the rules are for multiples of 6? So this is a chance to give Liz some advice if she was going to do this. What rule is it do you use to work out whether numbers are a multiple of 6. And here's a chance to share this in the chat. So I'll give you a minute or two to have a go at that.
Charlie, do you want them to put in their answer as well? What they think the largest 3-digit multiple of 6 is?
Ah, okay. Yes, so we've got 6 and 4 on the screen. Okay, give us the rule and then also tell us what you think the largest multiple of 6. Thanks, Claire. Good idea.
Okay.
Okay, overwhelmingly, it seems to be 864. So I'm going to type that in. And a lot of people were saying earlier that the reason is that it's got to be both a multiple of 2 and a multiple of 3. It's an even number, yes, and the digits add up to 18, so it's a multiple of 3. So that should be the largest one. Fantastic. Let's do one more, maybe make it slightly more difficult with maybe a few odd numbers. Okay, there we are. Do we have, can we get a couple of odd numbers? There we are, 1 and 5. What are you going to do with 1 and 5? Can you again, what's the largest multiple of 6? There's a mixture of 951s and 516s. And then somebody saying, but it's got to be even. So I think 951 is being discarded now in favor of 516. So 5 and 1 add up to 6. So I need another multiple of 3. So it looks like 516 is going to be the largest we're going to get. Fantastic. If, for example, you didn't type in a number that was a multiple of 6, for example, 514, you would get the feedback, this is not a multiple of 6. Okay. You'll notice that we skipped multiples of 4. So why don't we have a go at multiples of 4 next? Again, like we did last time, could you, and I'm talking to everybody rather than to Liz here, could you have a go at working, sharing what you think the rule is for multiples of 4? How do you know if a number is a multiple of 4? And then once you've done that, you might want to suggest what the largest multiple of 4 is that uses the digits 7 and 2. Okay, overwhelmingly 972 gets and a lot of people are talking about the last 2 digits being multiples of 4. So presumably because 100 is a multiple of 4, it's 25 fours, then 200 will also be a multiple of 4, and so will 300, 400, 500, 1200, 1500. a million hundreds. So we can sort of ignore anything beyond the hundreds column and just focus on the last two digits. So 900 is a multiple of 4. And if you add another multiple of 4 to 900, then you will still get a multiple of 4. 72, how do I know that's a multiple of 4? It's 8 less than 80. I know that 80 is a multiple of 4. So 8 less than 80 will also be a multiple of 4. So 72 is a multiple of 4. I suppose the other way I sometimes think about it is that I know it's got to be even, but I know that I've got to be able to halve it and then halve again. So half of 72 is 36, which is an even number. So I'm going to be able to halve it again. So that tells me it's a multiple of 4. So when I think of comparing 22 and 24, for example, 22 is even, but when I halve it, I get 11. So I can't halve it again. 24 is even, and when I halve it, I get 12, and I can halve it again. So if you're doing this work on dozens, you may want to have a look at an article that we've written called Divisibility Rules, where we talk about the rules for multiples of 2 and 5, 4 and 8, 3 and 9, and so on. And we explain why each of them works. So I know a lot of us know the rule for multiples of 3. When I was at school, I knew the rule, but it was a mystery why that worked. So we've got a nice explanation here of why it works. I was redoing the rule for multiples of 11 the other day, and I was saying to Liz, just what a lovely rule it is, and why you take the units digit and subtract the tens and add the hundreds and subtract the thousands and so on. And that's explained here. And all of a sudden, as well as having a rule, we have an understanding of why this rule works, which seems really nice. Okay, so this has been all too easy for everybody. So why don't we move to something slightly harder? We did multiples of 4, didn't we? So I'm going to go to the settings menu. And you can see here that our target number could be a 3-digit number, which is what we've been doing. And we've been offered 2-digit numbers, 2 digits. But one could say with younger students, start with a target number, which is just a 2-digit number. The computer gives us 1 digit, and we've got to choose the second digit. And later on, we could be thinking about 4-digit numbers where we're given 2 or 3 digits. What I'm interested in is thinking about multiples of 12. So sticking to a 3-digit number and being offered 2 digits. So again, what is the rule for multiples of 12? Would people like to share how they work out whether a number is a multiple of 12 or not? Rhiannon has just said in the chat, oh, I didn't notice the settings option. This is what's new about this interactivity, Rhiannon. There wasn't, in the original version of the interactivity, you could only do multiples of 2, 3, 4, and 6. And I think we get some interesting mathematical discussions generated once you go a little bit larger. Okay, a lot of people saying we need to make sure that the number is both a multiple of 3, because all multiples of 12 are in the 3 times table, but also a multiple of 4. And so a lot of people are suggesting 912. Let me just check. So this is a multiple of 4 because 12 is a multiple of 4, and it's a multiple of 3 because all the digits add up to 12. So that should be fine. That's worked out. We can do another challenge with multiples of 12, or we could go to the settings. I quite fancy doing another one with a multiple of 12. Let me see whether I can find one that is slightly harder than what you've been doing so far. Let's see. Okay, could you find the largest 3-digit? I'll give you 2 odd numbers. It was too easy earlier with evens, a mixture of evens and odds, I think. I don't know why Liz is smiling. Okay, someone's suggested 712. I don't think that's a multiple of 3 because the digits add up to 10. And somebody suggested 714. And my worry about that one is that the last 2 digits don't make a multiple of 4. So 700 is a multiple of 4, but the 14 isn't. So I don't think that's going to work either. 871's been suggested. Again, the problem with that is that it's not an even number. So it's not going to be in the 12 times table. 712 has been suggested, but the digits add up to 10. So it's not a multiple of 3. Shobna's writing to us in French. I don't know, Liz. A lot of people are saying it's impossible. Do you think this is because they're being lazy and they're giving up very quickly? Or do you think that they really believe, they think it's impossible?
Well,
Is this why you were smiling, Liz?
I think you're teasing, Charlie, but I think what is nice is that without you having said any more, people started off by tentatively saying, is it impossible? There's no solution. And now gradually we're getting a little bit of reasoning about why there might not be a solution. Yeah. And I think the vocabulary of solution answer is an interesting one. If there isn't an answer, is there still a solution? Because we can explain why there isn't an answer. But yeah.
Okay, so here's a challenge for everyone then. If you were doing this with your students, you know, what kind of justification would you require from them to convince the class, convince you that there actually is no solution to this? So somebody suggested proof by exhaustion, and that presumably involves doing something like saying, I know that multiples of 12 are going to be even. I've got 2 odd numbers, so I'm going to have to put an even one in the units column. So the 7 and 1 are going to have to go in the hundreds and tens, and I'm either going to have 7, 1 and an even, or 1, 7 and an even. So there's a limited number of possibilities. And Fiona's suggesting, okay, there's a limited number of even numbers that are possible because they need to add up to a multiple of 3. So 4 seems to be the only possible even number that's going to that can be added to 1 and 7. So we've got to try 714 or 7 or 174, and neither of them is going to work. So this is part of the benefit of this new interactivity, that we can go beyond the 2s, 3s, 4s, and 6s that we had in the earlier interactivity. And all of a sudden we have a discussion here about, I mean, we've gone into multiples of 12 much faster than you would do with children. You would spend much more time on 2s, 3s, 4s, and 6s than we have. And whenever you've got 2s, 3s, 4s, and 6s, you can always find a 3-digit number that satisfies the conditions. One way of thinking about why this doesn't work is to realize that 720 is a multiple of 12. And so the number before that is a multiple of 12, will be 12 less than 720. So it'll be 708. And so in effect, you miss out all the 10. You go straight from 708 to 720. And because multiples of 12 are 12 apart, it means that you're not going to hit any multiple of 12 between 708 and 720. And likewise, if you swap the 1 and the 7, why don't you get anything in the 170s? We know that 180 is a multiple of 12. So the one before 180 will be 168. And again, you go straight from 168 to the 180 and you skip all the 170s. So that's quite nice in terms of thinking about multiples of 12 being 12 apart. And part of the reason why in the settings we've allowed a 4-digit number where the computer gives us 2 digits is that all of a sudden you can work on multiples of 12. And if you're allowed to look for 2 digits, you've got 100 options and you will always be able to find a multiple of 12. Now, let me go to the teacher's resources and show you what we've written there. We've made some suggestions about what students might work on, including what we've just worked on, 3 digits, 2 digits, and multiples of 12. But you could be working with 4 digits, numbers provided 2 digits, and multiples of 200, for example. We just saw that 1 and 7 made it impossible to find 3-digit numbers. I'm going to just hide this away for a minute. There are other pairs of odd numbers that also make it impossible to find a 3-digit number. And some students sometimes think that that means that whenever you've got 2 odd numbers, let's go back to the problem. Whenever you've got 2 odd numbers, you're going to, let's go back to, it's going to be impossible. So, okay, so 7 and 3 is a pair of odd numbers, but I don't think 7 and 3 is impossible to do. So last question for you before we leave dozens. What would you add to 7 and 3 to make a multiple of 12? If you just want to stick it in, yes, in the chat. Okay, a lot of 732s. So 32 is a multiple of 4. So 732 is a multiple of 4. All the digits add up to 12. So it's a multiple of 3. And we can check. So one nice activity that we've suggested in the teacher's resources, and the teacher's resources are here on the left-hand side of the problem in the menu, is to ask students to work out which pairs of odd numbers make it impossible to find a multiple of 12 and which one don't make it impossible, aren't impossible. So there's that flexibility that that added challenge. At the bottom of the problem, we've got this rather wonderful problem, which is still about divisible multiples of 12. And every time I have a go at it, well, initially when I used to have a go at it, I didn't used to get the largest number. And so the show there is to warn people that if they get the number that most people get, they need to think again. So we don't give away the solution, but we do suggest that the more obvious solution is not the correct one. So you may want to have a go at this problem yourselves. I'm aware that Claire and I want to talk about two other problems. So Liz, is there anything else that we should want to add to say about dozens before we move on?
No, I think you've done a great job in cover everything there. I shall turn myself off and Claire can leap in.
I'm going to stop sharing my screen there, and then Claire can.
Yep. Okay, I've got a bit of a question for everybody. What I'd like you to do, I'd like you to think about two numbers that differ by 2, multiply them together and add 1, and then write your answer down in the chat. So that's two numbers that differ by 2. So it could be 1002 and 1004. Multiply them together, add 1, and then put your answer in the chat. And I'll give you a couple of minutes to do that. Yeah, it looks like nobody's going for my 1002 and 1004. Okay, it's got 81, 16, another 16, 25, 121, 36, 144, 81. Somebody's already answered the question that I was about to ask, which is, what do you notice about all these numbers? Apart from possibly, I can't know how to say that. 1, 2, 3, 2, 10 million, 2001. What do you notice about all those numbers? Got square numbers in capitals, just to be absolutely sure. Square numbers. So it looks like everybody has had a go at this, and don't apologise for the capitals. Charlie, would you like to share where this problem comes from?
Okay.
Yeah.
So let me share the screen again. Okay, so I'm going to go back to the teachers, secondary teachers page, and I'm going to click on the feature, and it's the start of Always Perfect. So Liz and I talked about dozens, and now we're talking about Always Perfect. If I'd gone to the secondary students page, it would look almost identical to this, except that the article isn't in the student. So we've included an article for teachers here, which we haven't included in the students feature. And Always Perfect has got, as part 1A, the problem that Claire just said to you. And because there's going to be a part 1B and part 1C and part 1D, which we don't want you to look at yet, so please don't be tempted to look ahead. We thought we would show you what we've put on the included in the problem. So we've got Charlie and Claire trying to explain what's going on here. So the Charlie character is representing the product of two numbers that differ by 2 as the area of a rectangle where the width is 2 more than the height. So you've got the diagram on the left, the rectangle on the left, and then the yellow strip on the right has been split into two. The right-hand half has been cut and added at the bottom of the square, and so we end up with almost a square. And so Claire asked you to add an area 1, and in this diagram it would be a little square of area 1, and that would then give us a square, and multiplying the two would give us the area of a square. So there's a diagrammatic representation, and Claire's got...
Yeah, which some people were doing in the chat.
Yes.
Yes.
So, yes.
I was thinking about this problem again this morning, and I think actually what I'd rather do, rather than n times n plus 2 plus 1, is I'd rather use n minus 1 times n plus 1. And this is something that you could talk with a group of students about. Here's another way of doing it. Which way do you prefer? I prefer the x minus 1 times x plus 1 because I find expanding brackets easier than factorising them. And it also sort of shows the gaps quite nicely. I'm going to ask everyone to do something else now. So I'd like you to think of two numbers that have a difference of 4, multiply them together, and then put your answer in the chat. So it could be 100 and 104, multiply them together, and then put your answer in the chat. So we've got 45, 21, 60, 48. I wonder which two numbers were 48. 140, 12, 5. I like that. Somebody's taken 1 and 5. That's a nice set of numbers. 140. Okay, so we've got a few numbers there. 27, 117. I'm not sure which two numbers.
27.
Sevens, yeah, I was trying to think of which two numbers that would be. Sorry, 96. So we've got a few numbers there. What would you have to add to all of those numbers to get a square number? Okay, 4 factorial. No, 4 exclamation mark. Yep, 4. So by having a look at this, we can then predict that if you've got two numbers that differ by 4, then we might need to add 4 in order to get a square number. Okay, so now thinking about another problem. Oh, somebody's asked why. Oh, we'll talk about why on that one first. So I'm going to share my screen now. I'm going to try to.
Yeah, I've stopped sharing.
Yeah. Okay, and hopefully this is going to work. Yep. So we've got two numbers that differ by 4. One way of using...
Claire,
yep.
I wonder, could you share the diagrammatic representation? Yes. And then we could ask everybody to do the algebraic representation of what you've just done. And when you finish doing that, I can return, or you can, to the explanation that we had when we did two numbers that differed by 2.
Yeah. So if I was trying to use the diagrammatic explanation, which is not where my mind naturally goes to, I'd start with a rectangle, which is n by n plus 4. I would chop off, well, I'm going to just divide it out like this, n and 4. Then what I'd want to do is I'd want to chop this in half, so that this is now 2. And I'm going to remove this bit here and move it down there. So that's 2. So my diagram is getting pretty small, but this is now n plus 2. And this across here is n plus 2. And then hopefully we can see what little area that bit is. We've had a couple of people who've had a go at working it out using the algebraic method already.
So can I just check, Claire, that little square that you're thinking of, what you're thinking of it as a 2 by 2 square?
Yeah.
And that's where the 4 comes?
Yeah.
Okay. And so before, in the example that we did originally, it was a 1 by 1 square, which gave us the 1.
Yeah.
Okay.
Okay, so if we were going to instead pick 2 numbers that differ by 6, what do you predict will be the thing that we have to add on to end up with a square number? And we've got lots of 9s. Okay, now for a different question. If we had 2 numbers that differed by 100, what would you have to add on in order to get a square number? Oh, we've got some different answers this time. Oh, and I think somebody's thinking about part 1D now. 50 squared. Yes, 2,500 is 50 squared. Yeah. So, Charlie, would you like me to share the diagram again on that one, or?
I can't work out whether to do the diagram or to do the general case, because at the end of the problem, we ask students to predict what's going to happen if you work out the product of 2 numbers that differ by 2k, and what needs to be added to them, to the product of these 2, in order to get a square number.
Yeah, so a few people are ahead of the game and have predicted what we're going to have to add on. If we were going to do it like this, then we get n squared.
So we would assume that by this stage, this is the kind of question that we would hope students would be able to, the drawing and the algebra. I mean, we've rushed because we don't have very much time, but
yes,
having done the first example and perhaps rehearsed the example for numbers that differ by 4, students hopefully will be able to do the general proof. But
yeah,
because we've rushed, do please do the
algebra.
Yeah, yes.
Yeah, yeah.
Yeah. And I might also ask you to do the drawing.
Oh, right, okay. Okay, so this would be n plus k squared, and somebody has already said they use problems like this when they're talking about completing the square. So we'd have to add on a k squared in order to achieve a square number. Using the picture, I'll see if I can draw a slightly better picture this time. I'm just going to have to move that slightly.
And we want to be clear about why it is that we get a k squared in the gap.
Yeah. So I'm trying to make this a bit bigger. So if this is n plus 2k, and this is n,
and we've chosen 2k because we've always asked for a difference of an even number in all parts to this question.
Yes, it all goes a little bit wrong if we start to use odd numbers. Well, it doesn't go wrong, but you You don't add an integer. Which is an interesting question to ask some pupils if they're finding this really easy. So we've got n by n plus 2k. If I split this in half, I get a k and a k, and this is still n. Then I'm going to take this bit and move it round. So this is now k. This bit has disappeared. So we've got an area of, or we've almost got an area of n plus k by n plus k. We're just missing this section here, which has got an area of k times k.
And so this fits in with the previous example where we had a difference of 100.
Mm-hmm.
And so a lot of people were saying, oh, the square that's missing at the bottom was half of 100 squared. So it was a 50 by 50. So that's why everyone was getting 2,500.
Yeah.
And for me, what's fantastic is that we start with something with two numbers that differ by 2 initially. And I suspect most students wouldn't have known that if you multiply them together, you always get a number that's 1 less than a square number. And I think the first time I came across this kind of a problem, I thought, well, is that really going to work even when I've got really, really, really big numbers and so on? And now we can predict what's going to happen, even when the numbers are 100 apart or, 5,000 apart. It feels so powerful and such a, but both the pictorial representation and then the algebra that represents it in the same way.
Am I sharing the problem now?
Yes.
Yes, I am. Yeah. Shall we go to?
Do you want to just scroll down just to show the part 1b, part 1c, part 1d are exactly what we've done?
Yeah. Shall we talk very briefly about part 2 now, or shall we go to a different problem?
Let's go to number rules, okay. Yeah.
Okay, so this is another set of problems which are fairly similar in feel to the one that we've just done. Number 5, shall we ask people to have a look at number 5 and see if they can think of a way to prove it?
Okay.
Yeah, so I'll just give you a few seconds to have a think about number 5 and think about how you might like to prove it. I unfortunately have now lost the chat.
Yes, I lost it when I was sharing my screen.
Yeah.
If you go to more.
Ah, yes, I've got it. Yes.
Then, yes, I was a bit alarmed when I was sharing my screen.
So think about number 5, and you can think about how you might solve it with algebra and how you might solve it by drawing a picture. This problem is called Number Rules OK, and you can also get to it via the secondary teachers feature. Okay, we've got somebody who's gone for the algebraic approach. Well, it's a bit easier to type into chat, I suppose.
So, do you want me to try and have a go at explaining the pictorial,
yep.
the image so yeah, I think it is much easier to share on the chat an algebraic explanation. So my image of what's going on is that if I've got a square, so I'm going to have a go at a numerical example. So, yes, okay, well,
you talk and I'll draw.
Okay. Okay, well, yes, no, so let's have x squared. So an x by x square. if I add to the right-hand side a 1 by x strip, and then along the bottom, an x plus 1 strip, I will get a slightly larger square. So this tells me that x squared plus 2x's plus 1 is the same as x plus 1 all squared. And I think that's the kind of thing that people have been writing in the chat.
Yes.
So if I remember correctly, Claire, when we were thinking about these problems, we were hoping that students were going to going to get used to representing what was going on, both pictorially and algebraically, and to realize that the algebra and the geometric representations could sort of talk to each other in that way.
Yeah, and in our Getting Started, which is a place where students can have a look for hints, we've got an example, which isn't one of the tasks on number rules, okay, but try and show how you might use a bar diagram to show that if you add 3 consecutive numbers, you get a multiple of 3. And we've also repeated that in the teacher resources, part of the way down here. Okay.
I'm aware of the time, Claire.
Yeah. Shall we very, very briefly talk about post 16?
Yes.
Yeah. So if you're looking for the, I am sharing the right screen, aren't I?
Yes, yes.
Yeah. If you're looking for post 16 resources, we don't have a separate post 16 students and post 16 teachers page. It's just the same page for everybody. If you click on post 16, then you can go to the latest feature. You'll notice that Always Perfect appears again. We've also got a question called Common Divisor, which is quite a nice question. And this links in very nicely from dozens. So the first question talks about evaluate 1 cubed minus 1, 2 cubed minus 2, 3 cubed minus 3. If you just think about 2 cubed minus 2 and 3 cubed minus 3, can you tell me what the largest integer that always divides those is? In our last 30 seconds. 6. Okay, so somebody said 6. So we think that probably these will all be divisible by 6. So then students need to think about, how can I show it's divisible by 6? If they've done dozens, then they'll know that it has to be divisible by 2 and 3. If they've looked at number rules, okay, they might have some hints about how they might show that. And we've also got some little hints inside the question that pupils can click on and reveal. This gets a bit harder with slightly different expressions, and part D is actually, I think, is really quite a fun question. So we'll leave that to you to have a look at as a bit of homework.
And can I just check, Claire,
Yeah.
the nice thing about factorizing n cubed minus n is presumably you get something like n times n squared minus 1. So you get n times n plus 1 and n minus 1. So you get 3 consecutive numbers.
Yeah.
And whenever you have 3 consecutive numbers, you must be getting a multiple of 3, and you must get an even number. So again, this links up a little bit to dozens, this idea about how many consecutive numbers you can go through without hitting a multiple of 3, or knowing that you're going to hit a multiple of 3. It links up to what we did about multiples of 12. So the idea of a feature is that all the problems are sort of linked up and related to each other. And using the algebra and thinking about the numbers at the same time. Yeah, we both got very excited about Common Divisor. And we've put the hints there so that if students sort of trip up at an early stage, they've got a little bit of scaffolding available that helps them move on and then try, part B and part C. We didn't want them to stumble and then and then stop at part A, in the hope that the hints will help them.
Just super quickly, going back to Always Perfect, we've said it's age 14 to 18. So far, the only bits that we've shown are GCSE level techniques. If you scroll down to part 2A, this is actually what the problem was originally before we started adapting it. You're looking at multiplying 4 things together and adding 1. So Charlie, we've got a Charlie's method and a Claire's method. Charlie looked at the numbers, tried to work out what the general solution would be, and then expanded, see if it worked. My method, I multiplied out some brackets, and then I tried to factorize them. If students are trying this problem, they can go to Getting Started again, and there's actually a little video to show how you might try and factorize a quartic. I think that's probably all we've got time for. Is there anything you want to add, Charlie?
No, I don't think so. Other than a lot of these problems are live, which means that they're open for solutions. I think they're going to be open for solutions. Let me check my diary, until the 15th of March. So if any of your students have a go at these problems, they can send us their solutions. We'll have a look at them, and then we'll publish some solutions the week after. It's always nice to receive solutions from students. And then hopefully students enjoy seeing their names being mentioned. And then we'll be publishing the next feature. And we'll do another webinar after the Easter break, introducing a couple of problems from then.
Yep. Liz, do you want to come back in and share your last bit?
Yes, I will. Thank you, Claire. Thank you, Charlie. There we go. So just to take you to the end of the session this afternoon, thank you all for participating. Just to remind you that you can keep in touch with us either via Twitter, using our NRICH hashtag for today's event, or the Twitter handle more generally. You may also wish to sign up for our email newsletter, which we send approximately once every half term. And that's the way that you will be one of the first to find out about events like these. You may also be interested, if you don't know about it already, in the secondary curriculum page. So this page on the site offers you a gateway into all the secondary tasks which are linked to the curriculum. In particular, you'll find there the secondary curriculum mapping documents. So they take objectives from the secondary mathematics curriculum and link them directly to NRICH tasks. So if you're not familiar with that page, do take a look at it. I did say that we're recording at the moment, and we will put up the video of this recording on that page, so /enrich-live-March 2021, and you will get a reminder about that in an email from Eventbrite as well. And finally, just to say thank you again to Trinity College for providing the funding for this event and the whole series, so that they're free of charge to you. We would really appreciate your help in making these events as as good as they can be. So please do send us your feedback via that link. Claire, if you haven't done already, and you probably have, would you mind popping that link into the chat? So
I've done it. Thank
you very much. Brilliant. One step ahead. So thank you, everybody. It makes such a difference that you participate enthusiastically and you make our lives a lot easier by doing so. We hope that we'll see you again at a future event. Thank you very much. Bye.
And I'll say goodbye in Spanish, because a few people have been saying thank you and goodbye in Spanish in the chat. So muchas gracias, ha sido un placer. Vuelvan el mes que viene. Espero que sus estudiantes encuentren trabajar en NRICH muy satisfactorio.
Just showing off, Charlie.
And a special hello to Sergio from Argentina, which is where I lived some of my life.